So here I'm going to talk about the very useful tool for the master of virtual work. So visual integration. So when we deal with the beam structures, we normally have the equation for the master of virtual work. So in this equation, normally EI is a constant. So we can move EI outside of this integration. So then we will have 1 over EI, 0 to L, small m, capital M dx. So basically, the method of virtual work is to evaluate the integration of these two. This integration comprised of two functions about x. So the small m is the bending moment in the virtual system. The capital M is the bending moment in the real systems. So if for the beam structures, for each bending moment if we're using one function for each, then this integration can be solved maybe in a short time. But for some beam structures applied by the concentric load or concentric moment, so then we have to use multiple functions to express these two bending moments. These two bending moments. So then we involve several. Then we have to divide the beam into several segments and involve the several. We have to have several integrations, and we also have to come out the expression for the bending moment as well. So this maybe take a long time to come out the expression for this integration. So here we can using visual integration to help us to solve this. So once we know how to use visual integrations, once we know how to use that, so if we know the bending moment diagram of the virtual system and the real systems, then we can apply the formula to come out the result of this integration in very quick. So before I do the derivation, I just want to talk about a very basic knowledge we will use in later. So it is about centroid points. So for area, the centroid point is the geometric center of that area. So we know for a triangle shown here, so the centroid point is this point. So this point to the distance from this point to the bottom line is the 1/3 of the height of this triangle shown here. And also the centroid point is on the line we draw from the top point to the center point of the bottom line. So this is a very common centroid point we used for triangles. So probably we all know that. But if we have a general shape, so the centroid point C on this shape. So how to get the coordinates of this centroid point? So we have two equations showing here to help us to calculate the coordinates of this centroid point. So in these two equations, we know so the numerator of this expression is x times dA. So dA is the small area on this shape. So the denominator is the area of the shape. So this is for the x coordinates. For the y coordinate is the integration involve y times the dA, okay, divided by the area of that shape. So this is the coordinate. This is the two equations to calculate the coordinates for a very general shape. So once we know that, let's do a rearrangement on these two equations. So if we put A on the left-hand side, for the A on the left-hand side, we got two new equations. So in these two new equations, we got some results for this kind of integration. So we will use in later to derive the visual integration. So once we know this, so now let's talk about our topic about visual integration. So So for visual integration, we'll basically deal with integration involve mx and mx. So here I just express a general case. So we involve two functions of x, fx and gx. So in particular, gx is a linear function expressed by mx times n, mx plus n. So if we just draw these two functions on the coordination systems, a general case is like this. So this line, this linear line is gx, and fx can be a linear line or non-linear line. So I just draw this curve as fx. So if we want to evaluate this special integration, we can put mx plus n into this integration. We got an expression for this integration. We have ab fx times gx expressed by mx plus n dx. Okay, so if we open this bracket, we got mx fx dx plus a to b n fx dx. Okay, so as we know, m and n are constant, so we can move m and n out of the integration. We got ab x fx dx plus ab n fx dx. Okay, so we got the two integration now. So let's look at fx times dx. What is this? So if we look at this diagram, so the fx is this curve. So the value, if we find arbitrary value, so on this curve is the value is fx, and if we draw a very narrow strip, so the width of this strip is dx. So then we can approximately say the area of this very small strip is fx times dx. So we can express this is dA, okay, the area. So this is a dA is used to express the area on this very small strip. So we can also say this is a infinitesimal strip. So once we got this, we know if we do an integration on the whole range from a to b, so we got the area a is expressed by this integration. Okay, so this area is just the a is just the area under this curve fx. So we can see here the two integration can be expressed by x, and fx times dx is shown here is dA. Okay, this first one, second one ab times the, so we put n outside the integral. So n fx times fx dx, this is dA. Okay, so we say this is the area of A. Okay, we just express over here. Once we know the value of the second integration, let's look at the first integration, x dA. So if we go back to look at the expression over here, so we know the x times dA, this integration is equal to the x coordinate of the centroid point of this shape times the area of that shape. So then we got here, we got m times x bar times the area of that shape times n plus a. Okay, so x bar is shown here. X bar is the x coordinate of the centroid point of this shape. The centroid point shown here is the blue dot shown here. So we got this. So if we do one more step, we got mx bar plus n times a. Okay, so look at here, mx bar plus n is basically x equal to x bar. So in this equation, so then we can express this mx bar plus n using gx bar times a. Okay, we call this very simple expression. So then for the integration fx, gx, dx. If gx is linear function, this integration can be expressed by gx bar times m. That is, the area under the fx times the gx, we value gx at the location of the centroid point of the area of fx. So let's look at it again. So if we want to evaluate of integration fx times gx, if gx is a linear function, so this integration can be expressed by gx bar times m times a. So a is the area under the curve fx, and on that area we can find a centroid point. So the x coordinate of that centroid point you will use to evaluate a gx bar. So gx bar. So that is, this integration is equal to the area under fx times the gx evaluate at the x coordinate of that area under the fx. Okay, so we can easily understand using these figures. So this is the derivation of this integration. Then we can use it to help us to come out a very useful tool about visual integration. So we will talk about in the second part of this video. See you later.